Now, oxidation by an oxidant in acidic medium. The oxidation could be potassium, the oxidant could be potassium permanganate solution K plus amino4 minus, potassium dichromate 2K plus Cr2O7 2 minus, or potassium chromate 2K plus CrO4 2 minus. This video shows the oxidation of primary, secondary, and tertiary alcohols by potassium permanganate in acidic medium. We have primary alcohol ethanol, secondary alcohol 2-butanol, and tertiary alcohol 2-methyl 2-propanol, and acidified potassium permanganate solution of purple color. We put in first test tube the primary alcohol, few milliliters of primary alcohol. Then we add few drops of acidified potassium permanganate solution of purple color, and we heat to accelerate the reaction. After a while, the purple color disappears, the solution becomes colorless, indicating that an oxidation takes place, because MnO4 minus of purple color is transformed into Mn2 plus, which is colorless. After a while, the solution becomes colorless. Now, for secondary alcohol, we repeat the same experiment. We take few milliliters of the secondary alcohol 2-butanol, and we add a few drops of acidified potassium permanganate solution, and we heat for a while to accelerate the reaction. And at the end, the solution becomes colorless. That means the 2-butanol is oxidized. The primary alcohol also oxidized colorless solution. Now, for the tertiary alcohol, we repeat the same experiment. We put a few milliliters of 2-methyl 2-propanol, colorless, and we add few drops of acidified potassium permanganate solution. Then we heat the mixture for a while, but the purple color did not disappear. That means no reaction took place. That means the tertiary alcohol did not undergo mild oxidation. Then no reaction. Primary and secondary alcohol, the purple color disappeared. That means there are mild oxidation, but in case of tertiary alcohol, no mild oxidation. The purple color did not disappear. Then the color of solution at the beginning of the oxidation is purple. The intensity of color decreases, fades till the solution becomes colorless. Disappearance of the purple color, that means the permanganate ions are completely transformed into manganese ion Mn2 plus, which is colorless. Now, this video shows the oxidation with potassium dichromate of orange color. We have primary alcohol, secondary alcohol, and tertiary alcohol in each test tube. We add in each test tube a few milliliters of the potassium permanganate solution, orange potassium permanganate, and you observe a change in color from orange to green in tube 1 containing primary alcohol and in tube 2 containing secondary alcohol. But in tube 3 containing tertiary alcohol, no change in color. The dichromate ion is transformed into chromium ion of green color, so that when we have change in color from orange to green, that means there is an oxidation that took place. Then primary alcohol and secondary alcohol underwent mild oxidation, while the tertiary alcohol did not undergo mild oxidation. The color remains orange. Okay, at the beginning the solution of potassium permanganate is orange, the alcohol is colorless. At the end the color becomes green if we have oxidation, because the orange dichromate ion are transformed to green chromium Cr3 plus ions. Now, oxidation of primary alcohol. As we know, primary alcohol, we have two cases. If the alcohol is in excess, controlled mild oxidation. The second case, when the oxidant is in excess, the mild oxidation of primary alcohol in excess leads to an aldehyde. Primary alcohol in excess plus, for example, MnO4 minus, it gives aldehyde and Mn2 plus. RCH2OH plus MnO4 minus give RCHO, C double bond O single bond H, aldehyde plus Mn2 plus. We balance this redox reaction using the half reaction method. First half reaction MnO4 minus give Mn2 plus. We know in acidic medium hydrogen is balanced by H plus and oxygen is balanced by H2O. We balance oxygen first, then hydrogen. But first we should balance the main atom, which is Mn. In this case, Mn, we have one Mn and one Mn in product, balanced. We have 4 oxygen reactant. We add 4 H2O in product, we have 4 oxygen. Now 4 times 2, we have 8 hydrogen atoms in product. We have no hydrogen in reactant. We add 8 H plus to have 8 hydrogen in reactants. Now for the charge, we have 1 minus and 8 plus. The total charge is 7 plus in reactants. In products, we have 2 plus. We balance the charge by adding electrons to the side where we have the higher charge, that means in reactant. The amount of electrons added equal to the difference between the two charges, 7 plus and 2 plus. The difference is 5, then we add 5 electrons in reactant side. This is the first half reaction, reduction half reaction. Now the second half reaction, the primary alcohol is transformed into aldehyde. We have carbon. In mild oxidation, the carbon chain is conserved. That means the carbon atoms is the same in the reactant and product. So we don't balance the carbon. We start balancing with oxygen. We have 1 oxygen and 1 oxygen balanced. Next, hydrogen, we have 2 and 1, 3 hydrogen in reactants. In product, we have 1 hydrogen, so we should add 2 H plus in product to balance hydrogen. Now, charge in reactant 0, in product 2 plus, we need to add 2 electrons to balance the charge. Now we have 5 electrons lost, gained in reactant, and 2 electrons lost in product. We should balance the number of electrons exchanged before start adding the 2 half reactions. We multiply first half reaction by 2 to have 10 electrons, and in second half reaction 5 by 5 to have 10 electrons. 10 electron reactant and 10 electron product cancelled. And the sum of the two half reactions, 5 alcohol plus 2 MnO4 minus plus 2 times 8, 16 H plus in reactants, and 5 times 2, 10 H plus in product. 16 minus 10, it remains 6 H plus in reactants. Give 5 aldehyde plus 2 Mn2 plus 2 times 4, 8 H2O. This is the balanced equation. Application 4. Write the balanced equation of the oxidation of 3-methyl-1-butanol by potassium dichromate in acidic medium. The alcohol is in excess. When the alcohol is in excess, then the primary alcohol will give an aldehyde. 3-methyl-1-butanol, butanol 1, 2, 3, 4, 1 butanol OH on carbon 1, methyl on carbon 3, CH3, then CH3, CH, CH2, CH2, plus dichromate Cr2O7 2 minus. Give the alcohol is transformed to aldehyde, only the functional carbon is transformed to carbonyl group. R remains the same, CH3, CH, CH3, CH2 remains the same, C double bond OH, the functional carbon transformed, and Cr2O7 2 minus gives Cr3 plus. Now we balance the H half reaction. First, dichromate give chromium. We have 2 chromium atoms in the reactant product. We have 1, we multiply it by 2. Now we have 7 oxygen in reactant. We add 7 H2O in product. We have 7 times 2, 14 hydrogen. We add 14 H plus in reactant. Now charge 2 minus and 14 plus, 12 plus in reactant. 2 times 3, 6 plus in product. 12 minus 6 remains 6 electron in reactant. Second half reaction, alcohol CH3, CH, CH3, CH2, CH2OH, give CH3, CH, CH3, CH2, C double bond O, single bond H. Balance of hydrogen, same number of carbons, carbon chain is conserved. 3, 6, 7, 9, 10, 12 in reactant. In product, 3, 6, 7, 10. We add 2H plus to have 12 hydrogen in product. Charge in reactant 0, in product 2 plus, we add 2 electrons. We have 6 electrons in reactant. In product 2 electrons, multiply the second half reaction by 3 to have same number of electrons, and the sum of the two half reaction is 3 alcohol, CH3, CH, CH3, CH2, CH2OH, plus Cr2O7 2 minus, plus 14H plus in reactant, and 3 times 2, 6H plus in product. 14 minus 6 remains 8H plus in reactant. Give 3 aldehyde, CH3, CH, CH3, CH2, C double bond O, single bond H, plus 2 Cr 3 plus 7H2O. This is the overall reaction. Now, second case, when the oxidant is in excess, continuous mild oxidation. The mild oxidation of primary alcohol when the alcohol is the limiting reactant, that means the oxidant is in excess, leads to a carboxylic acid. Primary alcohol plus amino4 minus in excess give carboxylic acid and amino2 plus. RCH2OH plus amino4 minus give RCOH. We transform the functional carbon CH2OH into carboxyl group COH plus amino2 plus. Amino4 minus give amino2 plus, 4 oxygen, then 4 H2O in product, 4 times 2, 8 hydrogen, then 8 H plus in reactants, 7 plus, 2 plus, we add 5 electron reactant. Second half reaction, alcohol give carboxylic acid. We have 1 oxygen in reactant. In product we have 2 oxygen. Then we balance oxygen by H2O by adding 1 H2O in reactants. Now we have 2, 3, 5 H. We have in product 1 H. Then we add 4 H plus. And charge in reactant 0. In product 4 plus. We add 4 electron. We have 5 electron reactant, 4 electron product. We multiply first by 4. And second half reaction by 5 to have same number of electrons to be cancelled, and the overall reaction then 10 electron in reactant, 10 electron product, 20 electron in reactant and 20 electron in product, remaining 5 alcohol plus 4 amino4 minus plus 4 times 8, 32 H plus in reactant, 5 times 4, 20, 32 minus 20 remains 12 H plus in reactants. Give 5 carboxylic acid, 4 amino2 plus, 4 times 4, 16 H2O, and 5 times 1, 5, 16 minus 5, it remains 11 H2O. Application 5, write the balanced equation of the oxidation of 2-methyl 1-propanol by potassium chromate in acidic medium. The oxidant is in excess. 2-methyl 1-propanol, propanol 3 carbon 1, 2, 3, OH on carbon 1, 2-methyl on carbon 2, CH3, CH, CH2, plus chromate CrO4 2 minus. Give. We transform CH2OH into COOH. The R remains the same, CH3, CH, CH3, COOH. And chromate into chromium Cr3 plus. The balance of the two half reaction, first CrO4 2 minus give Cr3 plus 1 Cr, 1 Cr. 4 oxygen, we add 4 H2O in products. 4 times 2, 8 hydrogen, we add 8 H plus in reactants. Now 2 minus and 8 plus, 6 plus in reactants, 3 plus in product, 6 minus 3, it remains 3 electrons in react. This is the first half. Second half, second half reaction, CH3, CH, CH3, CH2, OH, give CH3, CH, CH3, COOH, plus we have 1 oxygen reactant, 2 oxygen product, we add H2O to have 2 oxygen in reactant, hydrogen 3 and 3, 6, 7, 9, 10, and 2, 12, in product 3, 6, 7, 8, 12, 8 to become 12, we add 4 H plus in product, charge in reactant 0, in product 4 plus, to become 0 we add 4 minus, that means 4 electrons. We have 3 electrons in product reactant, we multiply it by 4 to have 12 electrons, and second half reaction we have 4, we multiply it by 3 to have same number of electrons 3, we cancel the number of electrons, and the overall we have 3 times alcohol, we obtain 3 CH3, CH, CH3, CH2OH, plus 4 Cr2O4 2 minus CrO4 plus 4 CrO4 2 minus. Now we have 4 times 8 32H plus and 3 times 4 12. 32 minus 12, it remains 20H plus in the reactant. Give 3 carboxylic acid plus 4 chromium ion plus 4 times 4 16 HO in product, 3 times 1 3 HO in reactant, 16 minus 3 it remains 13 H2O. Then the same process, the oxidant is Ml4 minus Cr2O7 2 minus CrO4 2 minus, the same procedure. Now, of a secondary alcohol, the mild oxidation of a secondary alcohol leads to a ketone. Secondary alcohol plus MnO4 minus give ketone plus Mn2 plus. RCHOH R prime secondary alcohol MnO4 minus give, we transport CHOH into C double bond O, RCO R prime plus Mn2 plus. Half reaction Mn4 minus give Mn2 plus H4HO plus H plus in reactants, 8 plus 1 minus 7 plus in reactant, 2 plus in product, 7 minus 2 remains 5 electron in reactants. Second half reaction RCHOH R prime give RC double bond OR prime. We have 2H in reactants, we add 2H plus in product, 2H plus 2 electron. We multiply the first by 2, second by 5, and the overall 10 electrons in product, 10 electrons in reactant cancelled. Now we have 5 alcohol plus 2 MnO4 minus plus 2 times 8 16H plus in reactants, 5 times 2 10 in product, 16 minus 10 remains 6 H plus in products, in reactants, give 2 ketone plus 5 ketone plus 2 Mn2 plus 2 times 4 8 H2O. Now application 6, write the balanced equation of the oxidation of 2-butanol by potassium permanganate in acidic medium. Okay, 2-butanol, 1, 2, 3, 4 OH on carbon 2, CH3, CH2, CH, CH3, plus permanganate MnO4 minus, give, we transform the CHOH into C double bond O, R CH3, CH2 remains the same, C double bond O, R times CH3 also remains the same, plus Mn2 plus. Balance the first half reaction, MnO4 minus, give Mn2 plus. We have 4 oxygen, we add 4 H2O. 4 times 2, 8 hydrogen, we add 8H plus. 7 plus in reactant, 2 plus in product, 7 minus 2, it remains 5 electron in reaction. Second half reaction, the CH3, CH2, CHOH, CH3, give CH3, CH2, C double bond O, CH3. Same number of oxygen, number of hydrogen, we have 3, 5, 7, 10 in reactant, 3, 5, 8 in product, we add 2H plus in reactant. reactant, 2 plus 2 electron. We multiply first half reaction by 2 to have 10 electrons, and second half reaction by 5 to have 10 electrons in reactant and product. The overall, we have 5 alcohol plus 2 MnO4 minus plus 2 times 8, 16H plus in reactant, 5 times 10, 5 times 2, 10, 16 minus 10 remains 6H plus in reactant. Give 5 ketone plus 2 Mn2 plus 2 times 4, 8H2. This is the overall reaction and the solution of application 6. Of a tertiary alcohol, tertiary alcohols do not undergo oxidation in acidic medium, nor catalytic oxidation, or dehydrogenation, since the functional carbon does not have hydrogen atoms. Tertiary alcohol plus MnO4 minus, no reaction. This is the mild oxidation of alcohol. Now, remark. Permanganate ion MnO4 minus can be replaced by dichromate ion Cr2O7 minus or chromate ion CrO4 minus in the oxidation of alcohol in acidic medium. The result of mild oxidation of an alcohol permits us to deduce its class. The following table resumes the mild oxidation of alcohols. If the alcohol is primary, by controlled mild oxidation when the alcohol is in excess, we obtain an aldehyde. When the oxidant is in excess, we obtain carboxylic acid. In case secondary alcohol, we obtain only ketones, and in case of tertiary alcohol, we obtain nothing. That means, according to the product of the oxidation, if we obtain aldehyde or carboxylic acid, then the alcohol is primary. If we obtain a ketone, then the alcohol is secondary. If we obtain nothing, that means no oxidation, then the alcohol is tertiary. Now, esterification. Alcohols react with carboxylic acid to give ester and water according to the general equation. Carboxylic acid plus alcohol, double arrow incomplete reaction, give ester and water. RCOH plus R prime OH give RCOO R prime plus H2O. From the acid, we eliminate OH, and from the alcohol, we eliminate H. OH from alcohol and OH from acid and OH from alcohol give H2O. The remaining RC double bond O from the acid. This is RC double bond O, the left of the acid, and OR prime are bonded together to give the ester plus H2. The characteristic of the reaction, esterification reaction, is reversible, incomplete, slow, and athermic. Slow, so that we should add a catalyst, H2SO4 as catalyst, and we heat the reaction to accelerate it. Now, case of primary alcohol. Primary alcohols react with carboxylic acids to give esters and water according to the general equation. RCOH plus R prime CH2OH give RCOO CH2 R prime plus HO. As we have said, we eliminate OH from the acid and H from the alcohol. The left of the acid RC double bond O, with O from this direction, the left of the alcohol OCH2 R prime, OCH2 R prime plus H2O. Example, CH3 COOH plus CH3CH2OH gives CH3COO CH2 CH3 plus H2O. We eliminate OH from acid, it remains CH3CO. We eliminate H from the alcohol, it remains OCH2CH3, OCH2CH3 plus H2O. Application 7, write the equation of the reaction between methanoic acid HCOH and 2-methyl-1-propanol. Solution: methanoic acid HCOOH plus 2-methyl-1-propanol, propanol 1, 2, 3, 1-propanol OH on carbon 1, CH3 on carbon 2. The reaction is reversible incomplete. We eliminate OH from acid and H from alcohol. It remains from acid H, C double bond O, from alcohol O, then CH2, then CH, CH3, CH3, and don't forget to write H2O. This is solution of application 7. Now, case of a secondary alcohol. Secondary alcohols react with carboxylic acid to give esters and water according to the general equation. RCOH plus R1CHOH R2 give. We eliminate OH from acid and H from alcohol. RC double bond O, rest of the acid. O, then CH. CH is bound to R1 and R2. This R1, this R2 plus H2O. Example: HCOH plus CH3, CH2, CHOH, CH3 give. The rest of the acid after eliminating OH is HC double bond O, O, HC double bond O till now. And by eliminating H, it remains from the alcohol O. We write O, then CH, CH. CH is bonded to 2R. The longest one is written on the line, CH2, CH3. The shorter one is written as a branch, and plus H2O. Application 8, write the equation of the reaction between propanoic acid C2H5COH and 4-methyl-2-pentanol. Solution: C2H5 C double bond O OH plus pentanol 1, 2, 3, 4, 5 OH on carbon 2, and we have on carbon 4 CH3. Double arrow. We eliminate OH, it remains C2H5 C double bond O from acid. From alcohol we eliminate H, it remains O. CH. CH bonded to longest one, CH2 from this direction, CH2, CH, CH3, CH3 on the line, and the shorter one, CH3 as a branch, and plus H2O. Case of tertiary alcohol. Also, tertiary alcohol reacts with carboxylic acid to give ester plus water according to the general equation. RCOH plus R1, R2, R3, COH give the ester RC double bond O from acid, OCH, C, R1, R2, R3 from the alcohol plus H2O. Example: C6H5COH plus CH3, CH3, COH, CH3. We eliminate OH, remains C6H5C double bond O from acid, from alcohol O, C, CHE, CHE, CHE plus H2O. Application 9, write the equation of the reaction between ethanoic acid and CHCOH and 2-methyl-2-butanol. Solution: CH3 COOH plus butanol 1, 2, 3, 4, 2-butanol on carbon 2 OH, and CH3 on carbon 2, CH3, CH2, CH3, double arrow, CH3, C double bond O from acid. From alcohol O bonded to CH, we write CH. CH is bonded to CH2, CH3 on the line, and left branch to CH3 plus H2O. Remark, for an equimolar mixture, that means the initial number of mole of acid equal initial number of mole of alcohol, the yield of the esterification of primary alcohol equals 66 to 67, 2/3. Secondary alcohol 60%, and tertiary alcohol 1 to 5%. This is the end of part 3, reaction of alcohols, and end of chapter 9, alcohols.